So now we will see some sequence processing approaches with deep networks. So, usually what we see so far are neural networks where the data is propagated in the network independently from the previous and following. We see an image, we do a decision, classify this image according to what it is. We don't have any information about, we don't use of any information about the previous images that we saw. Each decision is independent. So this is how we proceed so far. But in some cases, the notion of sequential data is important. So we may have to deal with a sequence of data, and the order we see the sequence may be quite useful and important for the task we want to achieve. And for that, I would say the classical model is what we call recurrent networks. So recurrent networks are networks where we have this kind of recurrent connections between the previous and the current steps in the sequence. And so this is different. Feed-forward networks, basically, we just have things that going like from the input to the output directly, like we saw with the multi-layer perceptron. While here with recurrent networks, we have this kind of loop connection here that is connecting the output at the current step, which will be used as the input for the next step. So we have this kind of looping over the sequence. And this is modeled like this here, which is relatively simple. We have the current input, we have the model that is processing it, and we have this output as modified to be the final output. But we also have this recurrent connection that gives to the model an input that is its output at the previous step. Unfolding it that way here, we've got this kind of processing where we've got the X in the sequence, so like the xt minus 1, xt plus 1, which are the different x's of our sequence. And then we see that, in fact, the ht plus 1 minus 1, so basically the value of h at previous step, is used as input for the current h, which is providing, in fact, the output for the decision ot, but also which is used as input for the next, the h for the next x, ht plus 1, and so on. So this is a way we are often like using it in practice. We are unrolling the network over the sequence. And the fact is that the weights here are shared over all the steps. So recurrent network is the classical model, but it's not the best one. It has several issues. One of the most important is the really limited capacity to memorize or capture things. It gets as input the output of the last iteration, last step. It is difficult to get information from many steps before. So it's kind of really having a short time memory. So the memory is quite limited and quite really based on the previous step or the previous few steps. So with LSTM, we are adding more explicitly a component of memory to the network. So we allow the neural network to memorize some elements and keep that memorized for several steps or many steps. So it's really useful for that. The way it works is that we have a memory cell. So basically, this is some kind of cell memory here with 4 neurons around it that are used to activate and deactivate. So all this kind of block, this kind of cell is managed with different gates, which gates are also, I would say, neurons. And the point is that we have mechanism to both like decide. So we have the input here. So the input is going into that. The input is used to control the gates. But also, we are controlling the use of the input into the memory. So we can memorize the input if the input gate is triggered. So if we are triggering it and at some level, then we will combine xt with the current cell value. We also have so this is basically the input activation here. We have also the forget gate, which have some kind of forgetfulness activation. Basically, it allows to erase the previous value in the cell up to some extent. It's not binary. It's more like, I would say, some kind of value that will damp a lot or not the cell of value of the previous step and replace it with the current value or the input value directly. So that's a different way to say we can just replace the current cell with the new input by forgetting everything and using the input directly as much as possible. And we also have the output activation, which is like mixing up both the cell memory values and the X value. So we can have some kind of pass-through somehow in the sense that, you know, we will, now in fact, we will have this gate that will kind of combine the xt with the memory in some ways and be multiplied directly with the cell value. So we have the cell, the memory value that is multiplied with the output gate that is combining somehow the x and the cell to make some value that is added or multiplied with the cell value, which is used as the output. So this kind of complex model, you know, we have weights that are learned both in the input gate, forget gate, output gate, and are managed in some ways to achieve some results. There are some variants of LSTM. We have things like bidirectional LSTM, because usual LSTM is processing in one way, just like the sequence from the beginning to the end. So that's good on several aspects. And so the memory is really kind of modified sequentially over the sequence. Bidirectional LSTM allow to get the sequence as a whole and making processing in both ways. So we have this process more like from the left to the right and from the right to the left, if we have things like a sentence. And so we have additional cells to process data in the reverse direction, and it allows somehow to capture in a more complex, elaborated ways the relation between the elements, because somehow processing one way may bring some bias towards some type of elements and not toward others. With bidirectional, we can capture more elements of the sequence and have possibly a better decision, but the cost is that we have more cells in our network, so the overall network may be more complex. So the bidirectional LSTM allow a better use of the sequence content. And as such, it is quite used for natural language processing. So this is a useful tool for NLP. Another variant, which is quite going the other way around, is a GRU, which is a simplification of LSTM, of unidirectional LSTM. So basically, it is combining the input activation with the forgetting. So this kind of more simplified model is useful. It is making a different trade-off between complexity and performance, because LSTM are known to be relatively complex. So it's not necessarily the easiest to use. So with GRU, we kind of going with smaller model, but that may hurt a little the performance. It depends. So maybe often it can be enough. In some other cases, we may require the complexity of LSTM. So LSTM are good to capture distant relationship in sequences, in the sense that with this kind of memory component compared to recurrent neural network, which are not able to capture distant relations in the sequence, LSTM is allowing to memorize some elements that can be reused later on after advancing when we are in a different step in the sequence processing. So that's good. That's the point of having a memory. And it has demonstrated to be quite versatile. So it's kind of can be used in different cases like automated translation, speech recognition, and so on. So this is a relatively general model for processing sequences. So it kind of controls much better the issue of vanishing gradient if we compare it with classical recurrent networks. Classical recurrent networks, we unfold it, and with this unfolding, we can see that, you know, the vanishing gradient problem can be a big issue, because we are not able to backprop over all the sequence, over all the copies of the neural network efficiently. While with LSTM, it is less an issue. However, LSTM are quite complex models. We have a high number of parameters. It requires long training times and large data sets. So it's not something we can use on small data sets. It's a resource-intensive approach, and it tends to overfit. So if we have small data sets, we can overfit quite well the sequences, which is not good in terms of generalization, but that's how it is. I mean, it's not. It has some capacity, but it really requires to be trained properly with enough data.